So hello everyone. I'm Adrien Prévost. I'm a PhD candidate at INSA Lyon, un laboratoire Ampère. And I'm working with Vincent Léchappé, Romain Delpoux, Xavier Brun on the synchronous rectification applied for small wind turbines. And today I'm going to synthesize two of my works, which are experimental comparison of passive and synchronous rectification on a small wind turbine and a wind turbine emulator. So I will focus today on the comparison because the wind turbine emulator is like a tool for the comparison. So just a little bit of context. So when I'm talking about small scale, I'm talking about under 20 kilowatt wind turbines according to the French classification. So these turbines, as you all know, they can power standalone off-grid systems or feed power to the grid. Here are a few commercial famous wind turbines here. And here's a locally manufactured small wind turbine, Hugh-Pigott design. Their drawback is well known. They are less competitive than their large scale counterparts because they have higher capital cost per power installed and a lower capacity factor. So from several decades, researchers and industrials make significant effort to optimize small-scale wind turbine in terms of cost, but also in terms of performance. Let's focus a little bit about on the small wind turbine Hugh-Pigott model, which is an open source model. So I'm working on this type of wind turbine because it's open design, but it also many advantages. So it ranges from 200 watts to 5 kilowatts at 10 meters per second. And the rotor diameter is from 1.2 to 6 meters, horizontal axis wind turbine. It uses a coreless axial flux permanent magnet generator, and in all cases they use a passive diode bridge rectifier. The advantage of this wind turbine is that they have a lower levelized cost of energy than commercial machines, good performance at low wind speed, and it's open design, so it's very useful for studying small wind turbines as a scientist. And also it's easy to maintain because as it is open design and there is some courses about maintaining these turbines, then the local communities, they can maintain these turbines. So let's have a look on the global energy conversion chain. All these blocks here are the different elements of the wind turbines. And all the arrows, they represent either efforts or flows. So blades, bearings, permanent magnet, synchronous generator, rectifier, battery, they all interact with each other. And all have a role in the conversion chain. And if we model the efficiency of each of these elements, so the CP for the aerodynamic efficiency, the mechanical efficiency of the bearings, the electrical efficiency of the generator, and the electrical efficiency of the rectifier. All these efficiencies are related to losses. So as leverage to increase efficiency, we can play on some of these elements. So some are playing with airfall, rotor size, pitch of the blades. Some are playing on the topology of the parameters of the permanent magnet generator. It's possible to co-optimize these blades and generator together. It's possible to add some passive filters to adapt to match the impedance between the generator and the load. It's possible to adapt the DC voltage at the rectifier by interconnecting DC to DC converter, and then to have a sort of control of the torque of the wind turbine. It's also possible to change the nature of the rectifier. And this is the leverage that we have chosen. So we've chosen a controlled rectifier and apply some machine control techniques, namely field-oriented control. So here is the problem statement. Today, can we increase the energy yield of locally manufactured small wind turbines with a synchronous rectification strategy? So here is our approach. The goal is, is to compare these two strategies with a fixed battery voltage and testing an identical generator with two different rectifying strategy, the passive rectifier and the synchronous rectifier. In the case of the synchronous rectifier, we need a controller because it is active. So we need some sensors to measure the currents of the lines and also the position. We'll see later that it's possible to do it without the position with an adapted observer. So how to compare the different strategies? What comparison framework to implement? So we'll see that during the presentation. So let's consider the small wind turbine system. So we see the blades, the axial flux permanent magnet generator, the currents, the rectifier, and the DC load. We have developed an active control strategies. And to test this control strategy, we have developed a wind turbine emulator. So basically what we did, we replaced the blade by a permanent magnet synchronous motor, which is controlled through a variable frequency drive, so that the torque of the blades is emulated, taking into account the inertia and the friction of the blades. I will not enter into more detail on how we did that, but you can, if you are interested, we have published a paper about this, and the reference is there. So we will use this tool to compare our strategies, and we will use the same generator. We'll see later that it might be a problem to use the exact same generator to compare both strategies. And then we compare the strategies, and this is what I'm presenting today. So here is the outline of the presentation. After this long introduction, we'll see the active rectification strategy. We'll say a few words about the experimental platform. We'll see the comparison frameworks. I will show you some results, and then I will conclude with some perspective. So this is the system architecture. Here is the topology, an electrical representation of the topology. So this is the representation of the generator electrical representation, and this is the active rectifier with the transistors, which are controlled with duty cycles, PWM duty cycles. And here is a very basic view of the control scheme, which is composed of 3 layers. An MPPT algorithm. Here we use optimal torque control, which gives a torque set point that we control with field-oriented control by measuring the currents, the lines currents, and the position of the rotor. So I'm talking about the angular position of the rotor, which is important to synchronize the currents with the position of the rotor to achieve a good control of the torque and optimal power factor. And this is transmitted to a PWM algorithm. Here we use space vector PWM. Okay, so a little word about optimal torque control. It's a very well-known method, which is robust, tolerant to modeling and uncertainties, have high convergence properties. We use this law because of these reasons. And also because it's well adapted for small wind turbines, because it's small wind turbines, they have a low inertia. So it's and the main drawback of optimal torque control is kind of delay that can happen during wind transients and the torque response of the wind turbine. But in our case, it's attenuated by the fact that small wind turbines have a low inertia. So that's why we use this. I will not enter into more detail, but anyway, let's focus on this graph on the left. These are the torque curves of the wind turbine according to rotational velocity, okay, for several wind speeds. When using a passive rectifier, the intersection of the black line with the different torque curves gives the operating points of the wind turbine for each wind speed. As it can be seen, it is not possible to perfectly match the impedance. So it's not, in other words, it's not possible to match the optimal torque with a passive strategy. With optimal torque control, we will use this simple law. So this is the torque set point that will control with the field-oriented control to obtain the optimal torque. Note that here the optimal torque is the torque that leads to the optimal power, which is different to the maximum torque. Okay, because power is basically torque times velocity. Okay, and the torque gain K here, it can be either the theoretical aerodynamic optimal torque gain, which can be calculated with the maximum CP and the optimal lambda, and also the swept area, and also the rotor radius. But in fact, this does not take into account the losses in all the conversion chains. So we are not sure that we are sure that it does not lead to the optimal power. But anyway, we'll see that in the conversion chain later. So we can see in the conversion chain that if we control with the gain that maximizes the aerodynamic power, we are not sure that we maximize the DC power. So there might be another gain, which we call here KDC, that maximizes the electrical power. Okay. So here is the experimental platform that we use. So this is the real scale locally manufactured small wind turbine generator, axial flux. This is a torque meter to measure the torque on the shafts, and this is the synchronous motor that we use to control to emulate the torque of the blades. And this is all the instrumentation. So active load. We use a DSpace micro-like box to acquire the signals and also to control the rectifier. This is the VFD, and these are the two different rectifiers, the passive rectifiers here and the active rectifier here. It's difficult to see, but they are there. So which comparison framework to use to compare both strategies, the passive one and the active one? Let's have a look into the voltage operating conditions of power transfer for both strategies. Okay, so let's define a ratio that we call M here, which is the ratio of the DC voltage divided by the amplitude of the phase voltage. Okay. For the diode rectification strategy, the power transfer can happen if this ratio is under the square root of 3. Otherwise, the diodes are not conducting. For the synchronous rectifier, if we want to use space vector modulation, that allows the maximum, that is the technique that allows the maximum voltage amplitude on the phase for sinusoidal voltage, then this ratio should be superior to a square root of 3, which means that these two ratios are not compatible, which means that if we want to use the same generator with the same operating points and the same DC voltage, it is not possible. Okay, so as in our framework, we'll use the same generator, we will be constrained to use a different DC voltage to test both strategies. So this is what the remark here. With a single generator, it's not possible to compare the two solutions with the same battery. So that is one contribution of our work, is to clearly evidence that if we want to compare the two strategies, either we choose a fixed DC voltage and two different generators, okay, or either we choose the same generator and we have to adapt the DC voltage, okay. So we have derived in our work an equation to find the adequate DC voltage for the synchronous at the synchronous rectifier for the optimal torque control law. Okay, so I will not enter into more detail here. And for the diode rectifier, it is known that the impedance matching is sensitive to voltage. Okay, so we have taken for the experiment different DC voltage to simulate the fact that the battery could be discharged or at full capacity. We used simply the fixed DC voltage. We didn't use a complex model for modeling a battery, but that can be something that could be done on that test bench. Okay, so we've taken some voltages from 22 volts to 28 volts. So here is the experimental protocol. We've used the fixed steady wind. We've used like static power curve measurements. So we've measured from 3 to 10 meters per second. So we focused on the zone 2, which is maximum power point tracking zone. We've measured the voltage current at the DC side of the rectifier and the torque at the torque meter and the rotational velocity. So that allows us to have the electrical power, PDC, and the mechanical power, PMecha. Then we compute the efficiency, the aerodynamic coefficient, and the tip speed ratio lambda. Then this allows us to calculate a truncated annual energy prediction from a static power curve, which gives us an estimation of the energy that we could harvest with each strategy. Okay. Okay, so I will show you now the experimental results. Generator rectifier efficiency, we define it as I said, the ratio of the electrical power divided by the mechanical power. So here, the red cross, the blue cross, the red star, the yellow square, and the purple circle, they represent the different the tests that we've done with the diode rectifier for each fixed DC voltage. We can see that the efficiency is maximized around between 4 and 6 meters per second of wind, which means that the work of impedance matching was well done by the designer of the wind turbine. And then vanishes a little bit, but it still stays good. As for the electronic rectifier, the active rectifier, synchronous rectifier, it's the blue and green and blue points over there, and they are systematically higher than for the passive rectifier. So which means that we have a better efficiency for all the wind speeds with the synchronous rectification. Okay. Then let's have a look to the power curves. So for the synchronous rectification, we have a better power curve for all wind speed, but we can see that between 4 and 7, we still have good performance with the diode rectification, but the simple passive rectification is very sensitive to battery voltage. Okay, we can see that the impedance matching is good for a charged battery, but is not good for a discharged battery. Okay, so interestingly, discharged battery will tend not to charge. At least it will charge in a less efficient way than a charged battery, which is a paradox. Let's have a look now to annual energy production. Sorry. The two scenarios with active rectification are there, and all the scenario with passive rectification are on the left. So from discharged battery to charged battery, we have increased from the annual energy production by 61% and by 19% for the minimum. We use the Rayleigh distribution at 5 meters per second average wind speed. I think that's all for the results. So now I will conclude. We've done a comparison of passive and active rectification for a 700 watt locally manufactured small wind turbine. Our experimental results show that the synchronous rectification strategy was more efficient than the passive rectification, and that the strategy led to increase the annual energy production by 19 to 61% in comparison to the passive diode rectifier method. We are working on some other aspects of the control strategy, which are adaptive maximum power point tracking. So finding which gain K of optimal torque control optimize the power output, but online. And we are also working on mechanical sensorless vector control. And we have submitted a work for publication in this field. So now let's try to take a step back from this. Our research question is active rectification relevant to small wind turbines in the off-grid context? Obviously, it is a trade-off between efficiency, environmental impacts, social impacts, cost, complexity. It's not an easy question to answer, but what we are trying to do to answer this question is analyzing the robustness of our sensorless observer, because we are doing sensorless mechanical sensorless control, not to complexify the mechanical design, so to avoid the need of a mechanical sensor which measures the position of the rotor. We also conducted life cycle assessment of the system. We are also conducting some socio-technical studies. And as a perspective, we will design a specific generator adapted to synchronous rectification to make some co-optimization. We'll perform some field testing with a real wind turbine. And finally, we hope to be able to optimize with multi-criteria optimization the machine rectifier subsystem. I was really happy to present this work to some small wind turbine expert today, and I'm very interested to have your questions. So thank you for your attention, and I hope I was not too long. I didn't have a look at the time.
from the digital or from the physical audience?
Is the...
Yeah, yeah.
Hello?
Hey, yeah. And it will be a technical question, I'm sure.
Oh, how could you know it will be a technical question, Daniel? Yes, because it was quite interesting. You, Anke here from the Folkecenter. I'm a little more technical.
Okay.
You know, you was concentrated to find the right load on the generator and the refrigerator and the charts. It was very interesting. But what is your strategy in the controller in the real world? Because I could see you have made a test in the wind tunnel from 3.5 to 10 meters or something, 4 meters. But in the wind tunnel, you're supposed to run, so you will let the wind speed go from 2.5 meters to 8 meters in 3 seconds and down again and up again. And as we know, is the rotor speed need to come up in speed, so it's compared with the wind speed. So if you have too much load on it, if you have full load on it, then it will probably take too long time. But what is your strategy to follow a quick up and down in the fluctuating wind where a small wind turbine is placed?
Thank you for your question. So just a little precision. We have focused on the zone 2 between cut-in wind speed and rated wind speed, which is between 3 and 10 meters per second wind. But the wind is actually played by the motor, which is there on the left. So we emulate the torque of the blades with the motor. Okay, so we are not using a wind tunnel. So this is for your first question. And for your second question, with this emulator, we were able to inject some turbulent wind. Okay, we did not share this work in today, but if you have a look at the paper about the emulator, we were able to reproduce the turbulent torque that is applied on the blades thanks to the emulator. And we use the turb sim from the Unreal to do that. And the strategy to control the generator, so to apply the torque on the generator, we use the optimal torque control. Okay, so we use the optimal torque control. I mentioned a very simplified 3-layer structure here. And this optimal torque control, the goal is to always apply a torque on the generator. So it's a negative torque because we are braking the generator, okay, which is proportional to the square of the rotational velocity of the wind turbine. And this particular law has a very powerful convergent properties, and which is very good for as a big wind turbine, but also small wind turbines, is that it enables smooth shaft loads, which is very important to limit the fatigue of the wind turbine. So, and why this? Because it uses the rotational velocity to compute that torque. I could go further, but maybe there are some other questions. I hope I have answered to your question.
Yeah, it was just you not kill the rotor. Okay.
Sorry.
Thank you. Any other question? Doesn't look like. No, sorry.
Have you done any estimation on how the cost would change of maintenance because you have added a switching component?
Thank you for your question. No, it's no, for the moment we are focused on the implementation of this, but we have not estimated. I think this is difficult to estimate this because we would need to perform some accelerated how to say it, aging of the components. And I think this is a bit tricky, and this is a whole domain in science to try to estimate that. But after a few years, maybe it's possible to determine how maintenance could increase. But it's very important question.
I think if there is nothing more, then we can move on. I would like to thank, wait, there is a question here. Is the efficiency calculation, I guess, left out radius? Can you just ask the question in audio? Maybe it's
yes, I will just show that here when we calculate the efficiency, we take the electrical power at the rectifier output, and we divide it by the mechanical power measured on the shaft. So the shaft is over there. It's measured. The torque is measured by the torque meter. Okay. And the rotational velocity also. So what we basically take as efficiency is the electrical power that goes to the load divided by the mechanical power that is there. So it includes all the losses between the generator and the electronics rectifier. I hope that answered the question.
Thank you. So I would say if there are more questions, we can take it a little later, or you can just chat directly to Adrian. Just remember not to chat to everyone, just directly to him, so then you can get the questions. Or of course, it can also be in the common chat, but then it pops up to everyone. It's a little distracting. So thank you very much, Adrian, for the presentation.